There is a bubble. Somewhere out there, right now, there may be a bubble. You can't see it. No telescope can find it. No instrument we've ever built can detect it. It moves at the speed of light. And when it reaches you, there's no explosion, no heat, no sound. The laws of physics that built your atoms, that hold your molecules together, that let stars burn and planets form, just stop, rewritten, between one moment and the next. This isn't science fiction. This is a prediction, a direct, unavoidable consequence of the best, most tested theory we have of how this universe actually works. And it might already be happening. We've gotten very comfortable with the universe. 13.8 billion years of stability will do that to you. The sun rises, gravity holds. Atoms don't spontaneously come apart. The coffee stays in the cup. The floor holds your weight. The sky is still there when you look up. It feels solid, reliable, like it was built to last. Here's the thing though, it might not be. There's a word in physics that sounds almost bureaucratic, metastable. Not a word you'd put on a movie poster, but it might be the most quietly terrifying concept in the history of human thought. Metastable means stable for now, locally stable, settled into a comfortable groove, but not at the lowest possible energy, not truly stable. There's a deeper state, a more fundamental arrangement. And if anything gives the right nudge, in the right place, at the right quantum moment, the whole thing falls. Picture that marble. It's been sitting in that bowl for billions of years. Every earthquake, every storm, every cosmic catastrophe it has held. To anyone watching, it looks stable. For all practical purposes, it is stable, but the ground drops away just millimeters from where it sits, and quantum mechanics doesn't care about practical purposes. Now imagine that marble is the Higgs field, and the hill it's sitting on is the fabric of the universe itself. For most of human history, we didn't even know to ask this question. It wasn't until physicists started building the Standard Model, the great half-century project of mapping every particle and force in existence, that anyone had the mathematical tools to even frame the problem. And when they did, what they found was remarkable. The universe we live in doesn't just happen to be here. It exists in a specific configuration, a precise arrangement of quantum fields that allows matter, chemistry, stars, planets, and life to emerge. But that configuration might not be the ground floor. It might be a very high, very comfortable ledge, with a long, long way to fall.
The universe appears perfectly peaceful, stable, permanent, and safe. But beneath this apparent stability, and that is the ultimate lie,
to get what vacuum decay actually is, you have to let go of something most of us were taught in school. The idea that the universe is made of stuff. It's not really. At the deepest level we've managed to probe, and we've gone incredibly deep, the universe is made of fields, quantum fields, invisible, mathematical structures that stretch continuously across every centimeter of space, through every galaxy, through every void, through you, right now, in whatever room you're sitting in. Every particle you've ever heard of, electrons, quarks, photons, the Higgs boson, none of them are tiny balls floating in empty space. They're vibrations in those fields, local disturbances, waves on the surface of something that extends to the edge of everything. Think of it this way: you pluck a guitar string, a vibration travels, it carries energy. In a sense, it is the music. But the music isn't the string is just the medium. Quantum fields are the medium of reality, and like any physical system, each field has what physicists call a potential energy landscape, a mathematical terrain of every energy state that field can occupy. When a quantum field settles into its absolute lowest energy state, that's called the vacuum. Not empty space, not nothing, the energetic ground floor of that field. Normally, everything falls toward the vacuum. Physics likes low energy states, but here's where things get strange. Some energy landscapes are complicated. Multiple valleys, multiple low points, and sometimes a field can get trapped in one valley, even though a deeper valley exists somewhere else. It looks like the ground floor, it behaves like the ground floor, but it isn't. This is the false vacuum. And the question that's kept physicists awake since the 1970s is almost unbearably simple. Is our universe, right now, at this exact moment, sitting in one of those states? Are we the marble? Physicists Sidney Coleman and Curtis Callan tackled this in the late 1970s. Through mathematics of staggering complexity, they derived the equations governing how a false vacuum decays. And what they found was this: quantum mechanics, with its fundamental randomness, its probabilistic heart, doesn't let false vacuums last forever. Given enough time, the quantum dice will eventually roll the wrong number. The field will tunnel through the barrier. The fall will begin. The question is, how long? And the answer changed in the summer of 2012.
Beneath the surface of our physical reality lies a continuous, dynamic quantum field. This is the ocean under everything.
July 4th, 2012. Two separate teams at CERN, Atlas and CMS, stood in front of a packed auditorium and said they'd found it. The Higgs boson, theorized in 1964, searched for across 5 decades, the quantum excitation of the most important field in the universe. Peter Higgs was in the audience, 83 years old, 48 years of waiting. He wept. The world celebrated, rightfully so. But in theoretical physics offices around the world, some scientists sat very quietly with a different feeling entirely. Not dread exactly, more like a very specific, very precise kind of concern. Because the discovery wasn't just a triumph, it came with a number: 125.09 giga-electron volts. That's the mass of the Higgs boson. And that number, that specific, measured, experimentally verified number, when you feed it into the equations of the Standard Model, alongside the measured mass of the top quark, it places our universe squarely in the metastable zone. Not stable, not unstable, metastable. The marble in the bowl, the ledge on the cliff. Let's slow down on the Higgs field for a second, because this is where most explanations skip the part that actually matters. The Higgs field isn't just a particle, it's a quantum field. It permeates all of space, every cubic centimeter of the universe, including the space inside atoms, including the space inside you, right now. And it has a value, a specific non-zero value physicists call the vacuum expectation value, roughly 246 giga-electron volts. That value is what gives elementary particles their mass. The electron has its mass because of the Higgs field. Quarks have their masses because of the Higgs field. The W and Z bosons, which control the weak nuclear force, have their masses because of the Higgs field. And those masses determine how strong fundamental forces are, how stable atomic nuclei are, what the rules of chemistry look like. Everything that makes matter behave like matter comes from that single number, the current value of the Higgs field. This field is why you exist. It's why atoms hold together, why chemistry works, why a carbon atom can bind to 4 hydrogen atoms in a specific geometry that leads, after 4 billion years of evolution, to something that can watch a YouTube video and feel genuine existential dread. And right now, that field sits in a state that is stable, but might not be the lowest state it could occupy. There might be something lower, a true vacuum, a state where the Higgs field value is different, where particle masses are different, where the rules of chemistry, the rules of everything, are different. The energy barrier separating our false vacuum from the true vacuum, if one exists, isn't something any human technology could breach. The LHC, for all its extraordinary power, isn't even remotely close. But quantum mechanics doesn't need technology. Quantum mechanics has time, and in an infinitely large universe, given enough of it, random quantum fluctuations will eventually create a region where the Higgs field spontaneously tunnels through, falls to the true vacuum, and when it does, it starts at a point, not a flash of light, not an explosion, nothing visible to any instrument we've ever built. Somewhere in space, in our galaxy, or the Virgo supercluster, or a billion light years away, or right next door, a quantum fluctuation occurs. The Higgs field in one tiny, subatomic region tunnels through the barrier, falls to the true vacuum. A bubble forms, and that bubble grows. What happens next is where this stops being abstract and becomes genuinely, physically staggering. The bubble wall expands at the speed of light, not approximately the speed of light, not 99%, exactly 300 million meters per second, the universal speed limit, the fastest anything can travel in this universe, which means there is no warning, none, zero, no signal, no radiation, no gravitational wave, no photon of light can travel from the bubble wall to any point in space and arrive before the bubble wall does. You cannot send an alert, you cannot build a detector that catches it early. You cannot look with any telescope and see it coming. The moment you could physically, theoretically, in any way detect its existence would be the moment it arrived, and by then, in an interval shorter than a single nerve impulse, you'd already be gone. For Earth, the whole thing would take 4 milliseconds. No heat, no impact, no sound. On one side of the bubble wall, a Tuesday afternoon on a blue planet circling a yellow star, children in school, oceans moving, radio signals carrying human voices across the sky. On the other side of the bubble wall, a region of space where the Higgs field has a different value, where particle masses are different, where the rules that allow protons to form, that allow electrons to bind to nuclei, that allow chemistry to happen, simply don't apply anymore. And this is the part that crosses from physics into something almost philosophical. The bubble doesn't kill you the way a supernova kills you. It doesn't incinerate you or crush you. It unmakes you. The atomic bonds holding your molecules together no longer follow the same rules. The electrons in your atoms have different masses. The electromagnetic force that makes chemistry work, the same force that keeps DNA holding its shape, that makes neurons fire, that makes your heart contract, it works differently here, not broken, just different. Different enough that nothing resembling complex matter could form, nothing resembling life could exist. Nothing resembling a question about the universe could ever be asked. In the ledger of the cosmos, it would be as though every atom that ever called itself alive had simply never existed at all. And the bubble doesn't stop at Earth. It doesn't stop at the solar system. It doesn't stop at the Milky Way. It expands forever, at the speed of light, in every direction, consuming every galaxy it reaches, rewriting the physics of every cubic light year it passes through. A true vacuum bubble, once formed, converts the entire observable universe, not in a dramatic climax, not in a grand finale, just steadily, silently, at 300 million meters per second, until there is nothing left but the word something could apply to. Okay, at this point, there's probably a very practical part of your brain asking one thing. How likely is this actually? And here's the honest answer. Extraordinarily unlikely, on any time scale we can meaningfully hold in our heads. The best calculations we have, using the measured Higgs boson mass, the measured top quark mass, and the full machinery of standard model quantum field theory, put the false vacuum lifetime somewhere around 10 to the power of 100 years, possibly much, much longer. For context, the current age of the universe is roughly 1.38 times 10 to the power of 10 years. Even the last stellar black holes won't finish evaporating through Hawking radiation until around 10 to the power of 100 years from now. The vacuum outlasts the black holes. On any human timescale, on any timescale a civilization could actually plan around, the false vacuum is effectively eternal. But think about what probability actually means when the universe is this vast. If the universe is larger than our observable 93 billion light years, and most cosmological models say it is, enormously so, then even a vanishingly tiny probability per unit volume per unit time, multiplied by an essentially uncountable number of locations, produces something approaching certainty somewhere. An event with one chance in 10 to the 100th power of happening in any given volume, in a universe with 10 to the 100th power times that volume, has already happened, not probably, certainly. The question then isn't if, it's where, and whether that where is inside our cosmic horizon. Sidney Coleman, whose 1980 paper with Frank DeLucia built the mathematical foundation for everything we know about vacuum decay, had a habit of opening his talks with a particular slide. It read, simply, "The information in this talk may be hazardous to your mental health." He meant it as a joke, mostly. Stephen Hawking returned to this topic again and again in his later work. In one of his final books, he wrote plainly that if the Higgs field sits in a metastable state, the universe is fundamentally impermanent, that a bubble of true vacuum could expand at the speed of light, and there would be nothing, no warning, no signal, no preparation possible. Now, there's a caveat that deserves its own moment. The standard model is extraordinary, but it's incomplete. It says nothing about quantum gravity. It can't explain dark matter. It doesn't account for why matter won rather than antimatter at the beginning of everything, which is the only reason the universe exists, rather than having annihilated itself at birth. Here's what we actually know, not what we fear, what we know. This universe, with all its complexity, all its fragility, all its improbably precise values, has remained stable for 13.8 billion years, not in some quiet protected corner, across a cosmos of 2 trillion galaxies. Through supernovae that outshine entire galaxies for weeks, through neutron star mergers that release more energy in milliseconds than the sun will produce in its entire lifetime, through galaxy cluster collisions on timescales of billions of years. And here's the thing most people miss. Cosmic rays have been slamming into Earth's upper atmosphere for the entire history of this planet. Particles arriving from astrophysical events, carrying energies that make the Large Hadron Collider look like a child's toy. Millions of times the energy the LHC can produce, every second, for 4 billion years. If those collisions could trigger vacuum decay, it would have happened. Billions of times over, long before life ever had a chance to emerge. It hasn't. Every quantum roll of the dice, across 13.8 billion years of a universe in constant, violent motion, has come up in our favor. There's something worth sitting with in that. Not comfort exactly, something more like perspective. We live in a universe that might be temporary, but every universe ends, eventually, in one way or another. What matters isn't the ending. What matters is what the universe managed to produce before the ending came. Atoms, chemistry, stars, planets, oceans, life, curiosity, questions. You, watching a video about the mechanics of universal destruction and finding it beautiful. That's not nothing, that's extraordinary. There's a strange peace available in all of this, if you're willing to sit with it. The universe that built you is 13.8 billion years old. It survived long enough to produce a species that could ask why it exists, how it works, and whether it's going to last. And we don't know if it will. We don't know if the vacuum is false or true. We don't know if the bubble is out there. We don't know if the standard model is complete enough to trust. We sit with uncertainty, the way the universe sits in its metastable state, apparently stable, locally stable, alive. If the bubble is real, if it comes, it arrives without warning, without drama. There's nothing to prepare and nothing to prevent, but it hasn't come yet. And in this window, this improbable, narrow, astonishing window of 13.8 billion years, physics arranged itself in exactly the right configuration to allow atoms and chemistry and oceans and brains and questions and you. Every time you look up at the night sky, every time you wonder what's out there and how far it goes, that's a living thing, built from hydrogen and time, asking the universe why it exists.